Hi there, this is Topic 8, Class 2 for MG5004 DE5418, where we're continuing on looking at vectors, but today we're going to look at multiplication of them and applications of vectors. We'll start by looking at multiplication of vectors. We've got two types. We've got scalar multiplication and it's written A dot B, or we talk about the inner product or the dot product, and the answer is a scalar. And later on in this video we will talk about the cross multiplication or the cross product. We'll probably talk about the scalar product, the dot product, and we write that as A cross B, and the answer to that is a vector. Multiplication of vectors translates into a useful tool for many engineering applications. I'm sure you've seen vectors used to break up forces and work done as well. The definition of a scalar product or the dot product or the inner product is A dot B is equal to A1B1 plus A2B2 plus A3B3. But how we need to be able to work it out is the length of A times the length of B times the cosine of the angle in between. You should recognize what we've got. A dot B equals length of A, length of B, cosine theta. You should recognize there that that's actually coming from the cosine rule. Let's have a look at an example here. If we were given that the length of A was 6 and that the length of B was 7, then the inner product or the dot product would be equal to, I'm just using the formula here, so it would be equal to 6 times 7 times cos of 60, and the answer would be 21. Obviously, the angle between the unit vectors I and j is 90 degrees, but let's have a look at a bit more at this idea of perpendicularity. So if we've got two vectors that are at right angles, then the angle between them is 90, and in that case the cosine of the angle between them will be the cosine of 90, which will be 0. So then the dot product would be 0. So we can prove that for I and j, the dot product between I and j, it would be the length of I times the length of j times the cosine of 90, which would equal 0. Let's have a look at I dot I. It would be the length of I times the length of I times the cosine of the angle between them, which must be 0, which would be 1 times cos 0, which would equal 1. Let's look at I dot k. It's the length of I times the length of k times the angle between them, which would again be 0. Let's have a look between j and k. So it would be the length of j times the length of k times the cosine of the angle between them, which would again be 90, which would be 0. Let's look at j dot j. It'll be the length of j times the length of j times the cosine of the angle between them, which is 0, so that would be 1. And lastly, let's have a look at k dot k, so it would be 1 also. Now, like so much of the maths, these things have properties. So a dot b is equal to b dot a, and a, the dot product of a and some vector with a scalar that's been multiplied by it would equal, as you'd expect, and we could even further rearrange that so that it's like that. And the distributive law, the distributive law also works. And a vector dot multiplied by itself must just equal the length of itself squared. In class we will do some examples involving this. If you remember from trigonometry, we would call OQ the projection of OP, which is the vector A, onto N, or more simply we'd be talking about the horizontal projection. So what we could say there is that cos theta is equal to the length of OQ divided by the length of vector A, so that the length then of the horizontal projection would be equal to the length of A cos theta. But also we know this. We know that where n is the unit vector of n hat is the unit vector of n, is going to be equal to this length of A times the length of the unit vector times cos theta. But obviously the length of the unit vector is 1. So what we've got now is that A times the unit vector of n is equal to the length of A cos theta. Since the length of the horizontal projection is also A, it's a funny theta, A cos theta, then A dot unit vector of n is equal to the length of the projection of A onto n. So what we've got here, this is the horizontal component of the vector A in the direction of n. As an example of this, let's find the component of A, where A is equal to 2i plus 5j, in the direction, I meant that to be 2i plus 3j j in the direction of n, and n is equal to I plus 5j. So the unit vector of n must be the vector divided by its length, because that's n over the length. So now we've got that the dot product is going to be 1 over root 26 times I plus 5j times 2I plus 3j, which is equal to 1 over 26, the square root thereof, times 2 plus 15, because you remember all the bits and things about I dot I and I dot j, etc., etc. So 2 plus 15 is all that we've got left, and obviously that's 17 over root 26, and 17 over root 26 is approximately equal to 3.334. So we've worked out, using vectors now, the length and got the answer 3.334. When we're now looking at planes, the only difference is that you'll have an I, a j and a k, whereas when we have a line we only have a unit vector in the I and the j directions. So to find the perpendicular distance from the plane, that's the blue outline thing, to the origin OB, this is the projection of the vector A onto the vector n. So the perpendicular distance is dot product A times n unit vector. And a couple of questions that we'll consider in class, but you can think about. Question 1 would be, are these two planes orthogonal? So are they at right angles to each other? And secondly, find the angle between 2I plus j minus k and 5I plus j minus 3k. So we'll do those questions in class, but please think about them as you go through the video. Now we're going to look at the vector product or the cross product, and what we've got is two vectors separated by an angle theta, and we define the cross product as A cross B is equal to the length of A times the length of B times the sine of theta times the unit vector E. And clearly the direction matters, as we'll see in the next slide, that A cross B is not equal to B cross A, it's equal to the opposite of B cross A. So just repeating again that the cross product of A and B is the length of A times the length of B times the sine of the angle in between times the unit vector in the direction of E. And it's the idea of a right-handed screw. So the situation that we've got is that the vector, the cross product, is perpendicular to the plane containing A and B. As I said before, direction clearly matters. Now some more on the unit vectors in each of the three dimensions, I, j and k. The angle between I and j is 90 degrees, so the cross product is going to be the length of I times the length of j sine 90 degrees times the unit vector, which is 1 times 1 times 1 times e. And this is where e hat is the unit vector that's orthogonal to I and j. And of course that must be k. So what we've got is that I cross j equals k, etc. If we look at the cross product of I with itself, what we've got is the length of I, by definition, crossed, times, but not cross times the length of I, times sine of the angle between them, which is 0, times the unit vector perpendicular to I and I. So that's equal to 0, because sine 0 is equal to 0. So you can work out the rest of them. Now the properties of these, properties of cross products, I've had the first one. And then the distributive law. As you would expect. So if we've got something involving all three of the unit vectors, the I cross I plus I cross j, and I cross I will be 0 and I cross j will be k, so our final answer would be k. What I want to do on this slide is prove the result that's written at the bottom of the slide and ignore all the twiddly lines. Right, let's start off with A cross B, and we know it's going to be, let's write out A and that's going to be crossed with okay, so we've got the vectors there, and now we can do A1I cross product with multiplied by all the rest. And then the next term would be plus A to J times the rest. Plus A3K times all the rest. And what have we got? We've got A1, B1, I cross I, plus A1, B2, I cross J, plus A1, B3 times I cross K, plus A2, B1, J cross I, plus A2, B2, J cross J, plus A2, B3, J cross K, plus A3, B1, K cross I, plus A3, B2, K cross J, plus A3, B3 times K, cross K. And if we deal with all of those and collect up the like terms and deal with the I cross I's, etc., etc., then the result is as it stands there. Now you might, or you should, think at this stage, well, I've seen that kind of thing before. And really it's now linking back into what we did with matrices. I'll insert a new slide. So what we've got is that if A is equal to A1I plus A2J plus A3K, and B is equal to B1I plus B2J plus B3K, then what we can write it as, and it's exactly the same thing, that A cross B is going to be the matrix, sorry, the determinant of the matrix IJK, A1, A2, A3, B1, B2, B3. For example, if B is equal to -1, 3, and 4, and C is equal to 2, 1, and -3, then B cross C is going to be the determinant of -1, 3, 4, 2, 1, -3, and we can work that out. That would be -9 minus 4 times I minus 3 minus 8 times J plus -1 minus 6 times K, which is -13I plus 5J minus 7K, and we could write that like that. We can find the area of a triangle such as the one given there, and we can say that the area is equal to 1/2 BC sine C, which you'd know anyway, and now we can rewrite that as 1/2 AC times AB sine C, which we can work backwards and say, well, that's the definition of the length of AC cross AB. And we'll do an example of that in class. You might like to look at this first, which would be to find the area of a triangle with vertices A, B, and C. Right, let's have a look here. We've got a straight line that's passing through A and B, and what we've got is that OP equals OA plus AP, and if we give them some names, R is equal to A plus some part of AB, which we'll call T, and AP is a multiple of AB. So what we've got now is that R is equal to A plus T times B minus A, because that's what AB is. And we could rearrange that so that we've got that R equals 1 minus T times A plus TB. Now, if I've got enough room, if C is equal to B minus A, then R equals A plus some number times C, and that gives rise to this. So we've got X minus A1 over C1 equals Y minus A2 over C2 equals Z minus A3 over C3, and that's equal to T. Or, putting it another way, put it up the top here. Putting it another way, we've got X minus A1 over B1 minus A1 is equal to, and all of these got vector marks, but it's just going to get a bit crowded. And all of that's going to be equal to T. And A obviously was A1, A2, and A3, and B was the same for B. We'll do some examples of this in class. To find the equation of a plane, we use the fact that the line joining any two points in the plane is perpendicular to the normal to the plane. So look at the diagram. The vector n is perpendicular to the plane, and A is the position vector of any given point A in the plane, and R is the position vector of any point P in the plane. So what we then end up with is that AP is equal to R minus A, and it's perpendicular to N. So that'll give us, because it's perpendicular, remember that if they are perpendicular then their dot product is 0. So R minus A times N is going to be 0, and if we just rearrange that a little, oops, I'll do one example in class, but I'll do an example here. Find the equation of the plane that's passing through the point with the vector 3i plus 2j plus 5k. So that's a plane passing through a point with the vector that I've given there, and it's perpendicular to I plus k. So the normal is going to be I plus k, and r times I plus k is going to be equal to 3i plus 2j plus 5k times n, which is I plus k, and r times I plus k, working out the right hand side, gives us that 3 plus 5, so that's equal to 8. So what we've now got is that xi plus yj plus zk times I plus k equals 8, and if we multiply that out, we get that x plus z equals 8, which is the vector equation of the plane that passes through the point, through the point with the position vector there and perpendicular to I plus k. What we'll do in class is we'll find the equation of the plane that's passing through these points. And see the third point. There's another video already on Moodle called Planes and Lines, and it looks at questions where you're asked to find the point where a plane meets a line and find the line of the intersection of two planes. So that's already in a video on Moodle called Planes and Lines.